So, um, you may have read a story recently about like how instructors are running into the situation where students don't understand like the idea of a hierarchical file system. People tell them, "Oh, find a file," and like they don't know what's going on. And this sounds like it's like it's the fault of somebody. I don't know who, but I think the expectations are probably lies that we've become inured to. And let me kind of explain this. Like I'm trying to think back to my first computer, like actually when I learned about files and subdirectories and all that kind of stuff. And I had a VIC-20, and that had a tape drive. Have you ever seen like the cassette tape drives? That didn't have files. It just whatever. Later on, I got a floppy drive. That was my first introduction to files, I guess. But it wasn't until I had like a Commodore Amiga that I actually knew something about hierarchical file systems. So, um, you know, how did I learn to understand that stuff anyway? So I don't remember. I messed around a lot. I bumbled around with it, and I don't know. So, um, so if the average student has to deal with it the way I did, of course they're getting lost. Up until my early years of college, I had a near complete lack of guidance with computers. Actually learning anything. That was how bad my education was. But you know, uh, I was somehow able to counter this by being like first extremely stubborn and second very socially awkward. So I didn't really have anything else to do with my time. So, anyways, I believe that there's like kind of a myth here, that the young people today just don't have basic skills. At least that's what this article, kind of implies. And I think the reality is that, why do we pretend that any of this was ever a given, and we've always seemed to rely on people just learning by bumbling their way through stuff. I mean, I should sound pretty familiar. So, one of the pretty important fundamentals of computing, at least for anyone like doing any kind of coding or whatnot, is like operating systems fundamentals. Like how do programs interact with the operating systems? And speaking of files and file systems, like how does that work? And how do they work with hardware? Like so, a little operating system knowledge goes like a long way. Now, the tradition, though, if you've ever been an undergrad in computer science, of course, like operating systems is typically this horrible undergrad course, like usually in your senior year of computer science. And the way you learn it is that you actually write an operating system to see what it does. And the crazy thing is that like not everyone gets it, right? It's like you get so knee deep into these details that you sometimes you just don't even get it. And basically carnage ensues. Like it's a very difficult course. It's known it's known to consume all your time when you have to take that course. But this really shouldn't be hard. You shouldn't need to write an operating system to understand what it does, right? Why limit it to a high level course? And you can learn and observe like a lot of this stuff just on the Linux command line interface. So I'm going to kind of talk about my approach for this, for teaching some of the basic system stuff. Maybe you've seen it before, maybe you haven't seen it before. I don't know. When I teach this in training courses, people seem to like it. So I just want to give my kind of philosophy of this. So my goal is just, show an approach for learning some, Linux internals. And I believe that it's really important to be hands-on. I think a lot of courses, you might see, people just, kind of talking about high-level concepts and this and that. I think it's really important to be hands-on when you're teaching this stuff because it's real. Like operating systems are very real. it's not like algorithms where, you take an algorithms course, you learn, 50,000 different algorithms, you never use them, operating systems, you're using those every day. So, but there's two goals here. One is like, if you're new to operating systems internal, you can follow along, and learn something. It's fun. Maybe it's fun. I don't know. But if you need to teach this stuff, or like you have like people who are trying to learn from you, like take note of the order that like I'm introducing the new aspects of the operating system, and also like the rate, and the level of detail, because so repeat later on in this talk, you don't want to be overwhelming with like how you present this stuff, because the operating system is vast. Not my goal. So what this talk is not about, is to tell you, I'm not going to tell you where this stuff should be learned, and when it should be learned. Like, so if you're looking for somebody to tell you that, you should teach preschoolers Linux, you got the wrong person. And there probably isn't one single person anyway. Like, people come to computing, from, all walks of life, all backgrounds, all educational backgrounds. And, they get introduced to this stuff at different times. And it's very, it's kind of an interesting question. So, but I'm not going to answer, because I'm not an educator. I'm just some slob, right? So first, lecturing 101, when you're teaching this stuff, you want to establish motivation and kind of get everyone on the same page, and this is where things get kind of like basic and weird. So you want to ask the question, like, why do we even have operating systems? Like, what's the problem that Linux is trying to solve in particular? And well, the answer to that, somebody might tell you, oh, the operating system solves, a lot of computing problems. There's tons of them, but you don't want to list them. It's really tedious, and it doesn't really convey the point. So we really need to take a step back even more. And this is going to sound like really, really basic. But here we go. So what is a computer? It's basically, if you look at the von Neumann architecture, you have a CPU, it does some computing, it has some memory, so the CPU diddles around with the memory, and then you have some IO like disks or network or whatever, and just to kind of get you into the Linux mood, I like to show people, okay, well, this isn't just like abstract, you just you go like cat's proc CPU info on a Linux system, you can see, you've got, a quite crappy processor here on this VM, but and you can look at the memory you've got, it doesn't hide anything from you. Come on. It tells you lots and lots of detail about memory. Don't worry, memory only gets worse. So, I can remember. So, we've got that stuff in Linux, right? So what do programs do? How many people have done assembly language here? Wow, that's more than I thought. But okay, for those of you who have not done assembly language, I'm about to ruin the mystique for you because it's really stupid. Basically, you have memory, and in memory you have instructions, and the CPU reads those instructions one at a time, and then it does, whatever. Like, and the instructions are like really stupid and basic. They're like, here you have like, over here you have like, say, address 2 and 3, add the values in there and store it in address 1. And most of, like, if you look at most machine code, it's just like, it's stupid stuff like this, or even worse, just copying stuff from one memory location to the other. Okay, so now we get to the problem. In these modern times, we want to have like multiple programs running, like we don't want to be cavemen, we want to be able to browse the web and, work on whatever at the same time, or have your 50,000 tabs open. How do we prevent programs from stepping on each other? Like, say program A and program B want to access address one at the same time. Usually, like if you try to do that kind of thing, like if you try to like write to one and read to the other, that ends in disaster. It all goes downhill from there. And that's my crappy comic book career taking off there with the PAL. So this brings us to what the operating system actually is. It is basically a big resource manager for running programs. It manages the CPU, the memory, and the I/O. That's its main purpose. And it kind of assists running programs so that they don't step on each other. Now, in Linux, a running program is called a process. Burn that into your head, if you don't know it already. A running program is called a process. And a really important thing about processes on Linux and almost any contemporary operating system is that they kind of think that they have the whole machine to themselves. Like they have this whole big chunk of memory that no one has access to. They can do whatever they want with the CPU. And to list this on your Linux machine, there's this PS command. You run PS by itself. It doesn't show you very much. You go run PSU, it shows you some more. And PSUX, that shows even more. And there are tons of options. So let's go to PSU. And I want to kind of talk about these columns here. So command is whatever program you ran, right? The PID is important. It's the thing that Linux uses to refer to the process. So you're not going to refer to processes by the command. You're going to use that PID, the process ID. And there's some other stuff down here, like the start time here. The time is the amount of seconds that it's been running on the CPU. This TTY thing that has something to do with typewriters, that's really horrible. Ignore these things because they might get you thinking about performance, and that's like the road to ruin. But I want to talk about these two. These are actually really interesting. So VSZ is the virtual size. It is the amount of memory that the process thinks that it has. So the process has started, it's asked for some memory. That's how much memory it thinks it has. It's like, okay, yeah, I'm good. If I ask for more, I'll probably get it, whatever. But the RSS is the resident set size. That's the amount of memory that the process is actually using at the moment. That's the amount of memory that the process resides in on the hardware at the moment, which is fascinating, right? There's a huge discrepancy now here. You see like this, whatever this first thing is. It thinks it has like this huge amount of memory, but it's only using like what, however much that is. I don't know. It's either 6 megs or something. Numbers, orders, magnitudes. Who cares? Yes, it does. But I'm trying to abstract that away because I don't want to throw in shared libraries. We're going to see shared libraries in a second, and it's horrible. So I like to kind of like to kick that can down the road. But it's a good point. But what I want you to take home from this is that yes, the process is being lied to. It thinks it has more memory than than it actually is, and it's actually very important that it's being lied to. Now, normally when I introduce this material, I also like throw in some stuff about some storage and block storage and some things like that. But I don't quite have the time for that in this talk. So anyways, so we've seen processes, we've seen PS, how to run it. Kind of a slow introduction and, a steady introduction to the lies that the operating system provides. And you might be asking yourself, okay, well, the processes are being fooled about the memory they have and where that memory is. And shared libraries are, a good example, because that's a tomfoolery of the the next level there. And another thing is that processes get moved on and off the CPU all the time. Like, if we have multiple processes running in a single CPU, which, you think you have multiple CPUs, but, in the old days, we only had one CPU and we still made it work. So, they get moved on and off the CPU all the time, yet they still think, oh yeah, I can do whatever I want with the CPU. And then finally, like, IO and files are available, like, we're kind of used to like being able to work with the network and working with a file, but who provides them, and who uses them? Like, what's doing this? And the answer is that the Linux kernel is doing this. We might be, heard of this mythical kernel. Well, this is what's doing all this management here, at least, on this basic level that I just showed you. So what it is, it's a really elaborate, management program. It massages the really ugly raw hardware into something that we can actually use. Now, here's the kind of funny thing about it. So it's not a process. It does include these things called kernel threads, which kind of act like processes, but I know this guy would knit about that, but I want you to ignore kernel threads because you can't do anything with them, at least not as a regular user. So here's a question for you. Like, how does the kernel run? The sort of the sequence and the way the kernel runs is actually really interesting. It's really important, and it introduces some very neat concepts. So imagine like we've loaded the kernel, the kernel's running and we have a bunch of processes going. But at the moment, the kernel has control of the CPU. So it runs, it does IO stuff, like it gets all stuff off the disk and does network stuff. Once it's done with all that, it chooses a process to run. So it's like, oh, this process here, it's ready to run. And then it kind of sets up the memory for this process. So remember I said, processes are being lied to. Well, at this step, the kernel is kind of setting up that make-believe world for the process to run in. And then the kernel hands the CPU off to that process. But before it makes that handoff, it says to the CPU, it's like, hey, I'm going to let you run this process for a little while. But after 400 milliseconds or whatever, I want you to come back to me. I want you to give me control back. So that's what happens. So the process runs. It does its adding 2 and 2 or whatever processes do these days. They show pictures of cats or I don't know. And then the CPU says, okay, you run long enough. So I'm going to grab control from you from the process and hands control back to the kernel. So the kernel then says, okay, I'm going to kind of save that process state. Remember I said there's kind of like a make-believe world. It kind of, saves the basics of that make-believe world. And then it kind of goes back to the beginning. And there are a couple, there are a couple important concepts in here. So this is basically how multitasking works. If you have several processes, that process that's running doesn't have to be the same one. It'll pick one process to run and I'll pick another process to run. So, that's called, that's a form of multitasking. And that's the true definition of that word, by the way. It was co-opted by business people who thought that it would be cool to apply to the humans. It does not work well with humans. So, origin of the word multitasking. When when the kernel chooses a process to run, that's called scheduling. If you hear like the term the kernel scheduler, that's basically what that what that is. It's just picking a process to run. And when you have, like, say you have one process and it switches to another process via this, you go through this, process A runs and then it comes back and then the kernel says, okay, I want to run process B. That's called a context switch. So if you ever heard the term context switch, that's what that is. Now, great, there's something really important about this diagram, in that you might notice this weird how I put the process all the way to the right. Why is that? Well, it turns out it has something to do with privileges. See, the kernel runs in something called kernel space. It's a special processor mode. And basically what happens in kernel space is that, the kernel can do whatever it wants to do. It can mess with any, mess with any part of memory. It can, it's basically God. But in user space, which is where processes run, it only has access to its own little piece of memory, its own little chunk of memory that it thinks it knows. And, in reality, it's not, one chunk of memory, it's in pages all over the computer, but let's just call it one chunk of memory because that's kind of how the process sees it. And, the process in user space does not have access to all of the CPU's instructions. It has access to most of them, but there are a couple, privileged ones that are not. So, if you've heard the term kernel space and user space, well, that's it. This is kind of a summary of that. The kernel has unrestricted access. User space has, they can only access their own stuff, and they cannot interfere with other processes. It's just like, it's user space is, per process. And here's another really important point. This really confuses a lot of people. Don't confuse users on a Linux system with, and how there's like this super user as well on Linux. There's this root user. Don't confuse this stuff with users with with kernel space, user space distinction. Like every process, whether it's running as root or not, is running in kernel space. Not in kernel, I mean user space. So every process runs in user space, except for kernel threads, but we don't talk about those. So, you run something as root, that's still running in user space. It cannot access the kernel memory, at least not normally. So why do we have this separation? It's basically safety. As I've been kind of like hinting at the whole time, like you don't want processes to go in, and step all over your disks, at least inadvertently. You don't want them to be able to step all over other processes, at least unless they mean it. Ideally, if in computing, when we think of when to run something in kernel space, it's generally best to run whatever you can in user space, if possible, because it's safer that way. This is not always done in practice, but people aim for that direction. Basically, the less code in the kernel you have, the greater your system stability is. I don't know if you've seen the Linux kernel source code these days, but it's quite large, but it's tightly controlled. So, user space and kernel space define. I think we have a good idea what the kernel is and kind of what it does. Now I want to start on kind of talking more about processes themselves. And this is kind of the life and times of a process, right? So basically the process gets created somehow and it starts and then it does its normal user space computation, adds 1 and 1, gets 2 and shows cubecats or whatever. But occasionally the process asks the kernel to do something. Like it might want to look for a file or, access the network or something. So the process will ask the kernel to do something. And then at the very end, once the process has, finished and terminated, it leaves this thing called an exit code. And I'm going to do this a little bit backwards. You might think, well, you should start at number 1, but actually number 1 is the most complicated of these. So I'm going to start at number 4 with exit codes. An exit code is just a number. It's an integer number, and the exit code of 0 usually means success, and non-zero usually means there's an error code. There are exceptions to this, but they're like grep in a couple other programs, but they're really rare. So in the shell, the exit code of the last process that ran is in this $? shell variable. So let's try that out. We're going to go, oops. So I'm going to just create some file, right? Put some junk in there. And then I'm going to go cat file. And then I'm going to show the exit code. And this 0 is the exit code of cat, like the cat command, which is 0, means yes, it's successfully displayed that file. However, if I do something like this, if I try to cat some file that does not exist, first I get the error message, but then if I do a echo $? I get a 1. That's the error code. But there's a gotcha here. If you are writing shell scripts or something like that, and you need to get that exit code, get it right after the exit code, the last process runs. Because if I run this again, I get 0, because this exit code here refers to this command here, not this one. So it's always the one directly before it. So I did a cat something doesn't exist. Exit code. I looked at the exit code, but the program that I used to look at the exit code exited in success. So it became 0. Okay, so exit codes. Great. It was pretty simple. Now, remember I said occasionally the process needs to ask something for something from the kernel, like to open a file, to ask for more memory, to access something on the network, or to start another process, kind of getting ahead of ourselves here. But basically what a system call is it's a very strictly regulated request from a process to the kernel. So the process formulates this this request, and then it hands it off to the kernel in a very controlled manner. The kernel looks at it very, very closely, because the kernel doesn't want any funny stuff happening from processes, and it will it'll throw away anything that it won't throw away, but it'll return an error from anything that it's not allowed to do. So let's look at some system calls. This is always kind of fun. So in Linux, there's this trace command. It's called system call trace. And if I just do trace, what was that file called? Some file. I get this. Oh my God, it's crazy. It's like all this junk. And most of this junk on the screen you see here are system calls that relate to shared libraries, setting up shared libraries. It's a mess, but you have to deal with it whenever you are tracing system calls. But I want to just get the meat here, show you what's really important, what the cat program's really doing. So right here, this system call is a version of the open system call. We're opening that file, that some file. We're getting this 3 back, which is called a file descriptor, which I'm unfortunately not going to talk about today. Then we read from that file descriptor, we get that stuff, and then we're we're writing what we got back out. So that 1 is actually, that's standard output, which I'm also not going to get to. And then, there's nothing left to read. So we're going to close that file and we're going to exit. You remember the exit code that I just talked about? That's the system, that's kind of like the exit system code. I'll call that return 0 and gives us our exit code of, of 0. It'd be nice if I could type one of these days. And this is really fun to play with. Like, if you know basic Unix commands, you might be interested to know what some of these system calls are. But one I'm going to talk about, one other one I'm going to show you real quick is the RM system call for removing a file. Is this one's fascinating. Notice this is it right here, this unlink thing. So you may be wondering, like, why is removing called unlinking? It has something to do with the file system, and that'll be, like a further topic that you can either like look that up in my book or, look it up somewhere else because we don't have time for it right now. So, wow. Okay. System calls. Now going back, remember our process lifecycle, I'm going to skip over doing normal user space computation because it doesn't really have anything to do with the kernel. So now I want to talk about, creating and starting processes. So how do we do that? Well, sort of a traditional way in Linux is that there's this fork system call, and it tells the kernel to duplicate the current process. So you call fork from a process, and you end up with another process that's pretty much doing almost the exact same thing. After completion, the original is called the parent process, and the duplicate is called the child process. So you've heard the terms parent and child process. This is where it comes from. And as I said, it's still the same program, still running the same thing. So that looks kind of weird. You might think, well, can I do that interactively? And interactively, it looks kind of weird. If I go import, hopefully you all get, if you don't know Python, you kind of get the idea. If I go os.fork here, I actually get like 2 prompts back and 2 return values. That's because there's there are now 2 Pythons running, and they can fight over like I'm trying to type things here, and they're actually fighting over the input of the prompt there. So that's like let's see, make sure I got rid of that thing. Yeah, okay. So that interactively, it's a little bit hard to show fork like that. But I want to kind of move on from that. Just keep that fork thing in mind. You're thinking, okay, well, that's the duplicate of the current process. Well, what if I want to start some entirely new program? Or there's this other system call called exec. And what that does is it asks the kernel to run an entirely new program in place of the current one. So the process ID stays the same. It's still the same process for the most part. Like we'll have different kind of memory memory characteristics, but it's just running something else. And this is very common in shell scripts and some other programs. So let me show you that. That's much easier to show interactively. Come on. If I go os.exec the hopefully, this is a little more complicated than other system calls to set up because the kernel needs to be very careful about it. So what's going to happen here is, you notice how I have a Python prompt here. I started at the shell prompt. I went to a Python prompt. Well, what this is going to do is it's going to run ls, and then that Python prompt is going to go away because this ls is going to take the place of the Python. You see, I got my shell prompt back. So that's that's exec. Now you're thinking, well, to start I want to keep my old process around, but I want to start a new process. Kind of the obvious thing here is that you run fork and exec together. So you run one and you run the other, and the idea is that you call fork, and then you call exec in only the child process. And this is kind of what's happening when you run almost anything in the shell. This sort of this sort of flow here. It's like, it forks, the kernel says, okay, I'm making a duplicate of you. And then in that child, the child is programmed to know that it will run exec to start something new. So I'm going to show you that. Again, in Python, because it's pretty easy to show this in Python. So if I go def run ls, create some new function, and I go os. Oops, I want to go pid equals os. Oops. I should mention that if you are doing this in Python, like, use subprocess. Like, don't do it this way. Use like one of the more managed and one of the more managed packages. But this is what's happening under the hood. So we go if pid is equal to 0. Now, remember how fork duplicates itself, and so you have 2 copies of the process at this point. And the biggest difference at this point is that the return value of PID is different in the parent and the child. In the parent, it's the process ID of the child. In the child, it's 0. So here, we know we're in the child. So we go, oops. And sorry about this flashing. This computer is not very good. So, and then I'm just going to return this statement here will only run in the parent because this one will cause the child to go away. Okay, so if I haven't mistyped anything, I can go yep, missed the colon. I think that's like one of the, I shouldn't say it's not the first time that that's happened, but anyway, so if I go like run ls now, I guess that's what I called that. Now you can see, I got the ls there, although my child process, that ls was PID 6534, and I have run ls.py, but there's one interesting thing here to point out. This is going to be a kind of our last technical thing here. So I go PSU. Notice I have this thing here near the bottom, this sort of a thing called this ls that says defunct here. And you're like, that's terrible. Like, why didn't my process go away? Can I kill it? Right? So that was 6534. Oh, it's still there. What if I like really kill it? I'll do it like this to, give it emphasis, like all caps like that, They're like, oh my God, it's still there. What's happening? Well, that's called a zombie process. And the reason that exists is because the kernel expects the parent to collect the exit code of its child when the child exits. So to do that, in Python, you could just go to os.wait. And now, do a PSU. you can see that that thing went away. All right, but now, okay, so let's kind of talk about progression a little bit, because I've started, I've now introduced some new stuff, and you'll notice that I kind of relied on that stat column of PS. You might be wondering, well, what is that? Well, that's the process's status. Real quick, S means sleep, T means stop, R means running, and Z means zombie, and there's a few others. But this is kind of like stepping back to teaching and learning. This is like the next thing that I teach in, when I introduce this material. This is the next thing that I do. The process states are next. And I don't think, right, because we're almost out of time. I timed this so that we would not have time for this. So you might be wondering, what is that stuff in the PS stack column? So yeah, process states is next, and that's where I move to next when I introduce this material. And then finally, you saw how I tried to kill it with that kill command. Well, that's signals, and that's the final topic that I give when I teach this material. It's a nice next step. But yes, I'm only introducing like one basic concept at a time, and I'm not trying to overwhelm people with the shell and command line, like throwing like MV and R, all this kind of stuff. Just one little thing at a time when I'm teaching this, just to kind of build it up. But there are some pitfalls here. First of all, like starting at the bottom, like going, that can be problematic if there's some details are just too plain tedious, right? Like certain explanations of hardware will be just pointless. So I say, like this is kind of the teaching part of it. Try to keep things relevant to what you'll see in real life. Like, can you illustrate it on the command line? If you can, great. Maybe it's something to include. And then to kind of give you a further idea, I usually teach this stuff. Like I originally kind of developed this as sort of like a training, like a 3-hour, 3-part training regimen. First was the introduction to the kernel and process, which you just saw, kind of walked you through how that works. The second part is storage and file systems, kind of giving you an idea of how like storage works and block devices and how where file systems fit on there. And then the third part, I bring those two together and bring the processes that you saw from part one with the files in part two. And that brings us to the file descriptors, which I also sort of introduced when I showed you the strace. Remember the strace cat command I did? I talked about file descriptors. That's where we kind of get like more hands-on and like really are able to define what a file descriptor is, what standard IO really is. And then to kind of finish it off, I do I introduce inodes and links. Remember the RM command, how it was like you had the unlink command for removing a file. Well, that's what's in there. And then finally, symbolic links, because symbolic links are just maddening and different than other links. So then you're set to start learning more, like learn what users really are as opposed to user space. This thing called the FHS, you're getting more and more into user space. Booting, like how does the kernel boot? Like how does user space boot? Memory, which is kind of a crazy topic actually. System metrics, if you're obsessed with performance, you can look at that. And networking, which is kind of its own little different world. But if you kind of like have the idea for how things are built up, step by step, as you saw here with the kernel, networking kind of works the same way. So that there's that kind of stuff is all in the book, by the way, in my book, by the way, which I don't really promote very much, but so my final words of advice, if you're learning, Like, don't avoid basics because they like seem impractical, because they can actually be quite, they can tell you a lot about what's going on, and really don't be afraid of getting your hands dirty, like, mess around with your computer. Like, don't be afraid of screwing it up, because it's usually screwing up your computer is the best thing you can do. And if you're teaching, don't overwhelm your students, and always get your hands dirty. Always be hands-on, and always demonstrate it in in real terms. So that's all I have.